Yeah. So first we calculated that we have two charges, right? And then we calculated what is, so they are separated by some distance, let's say r. So what is the electric potential energy? And then we calculated it to be k q1 q2 by r, right? So this was the potential energy that we calculated. And then if we have numerous charges, right? So then your in potential energy would be summation of I, j, and I not equal to j, right? And then this is what? K. K we can take outside, but qi, qj divided by rij. So this is the potential energy due to different multiple charges. So let's take an example of let's say this triangle. So this we did, and we also did one problem, right, Aisha and Mariam? So,
Yes,
let,
sir.
so let's say this is Q1, Q2, Q3. So the potential energy would be first this one, and the rest this one. So first would be, let's say this is R1, and in this notation, let's say this is R12, this is R13, this is R23. So you would be how much? K Q1 Q2 by R12 plus K Q1 Q3 by R13, and plus K Q2 Q3 by R23. Right, so this was the potential energy. And why this half comes? Because we have not written that factor. So K Q2 Q1 by R21. This is same as this one. So that is why this half is there. Okay. Now the next topic is the potential energy due to the, so potential energy in external electric field. Right. So let's say that we have this uniform electric field, and its magnitude is E, right. And then we have two charges. Let's say at here Q1 charge, and at this place Q2 charge. And this is the distance between them. Let's say R. Okay. So if this is an electric field, then this point would have some potential. So let's say that it has V1 potential, right? And let's say that it has V2 potential. Okay. So we know that work done is QV, right? Right. So the potential energy would be due to this potential, right? And this potential and the interaction between these two charges. So I will just directly write the formula, right? This would be simply Q1 V1 plus Q2 V2, and the interaction K Q1 Q2 by R. So just remember this. Whenever you have external electric field and you put two charges, so then these two factors will add up, right? Because otherwise, if there were no electric field, then there were no potential, right? Then these parts were zero. But if we have this electric field, which is giving some potential at this point and this point. So that is why these two terms are coming up. Okay. Is this clear, guys? Yeah, clear. Doubt? Any doubt? Question? No doubt. So you guys please note it down, and then we will talk about electric potential energy due to dipole. Yes. Yeah. So we have this external electric field, right? And due to this electric field, there would be some potential at this point. So we know that what is the work done in the external potential or work done in some potential? This is Q into V. So we calculated due to 2 point charges without the presence of some electric field, we calculated this work done and this work done, right? And these work done combinedly gave us the total work done, which was k q1 q2 by r. But this had some zero work done at a point and let's say at b point, right? Now, because we are in some external electric field, so this will not give this work done to be zero, right? You will have some work done at this point, which is what? Q1V, right? And then we have some work done at this point, which is Q2V, Q2V2, right? And then you have this internal interaction between Q1 and Q2 charges. So due to this, we know that this is the potential energy. But due to the external electric field, there would be some extra work done. Q1 V1 and Q2 V2. So these will also add up in the potential energy part. So is this clear? Is this clear, Aisha?
Yes, sir.
Okay, please, did you guys note it down? Yeah, noted.
Yes, sir.
Okay. Now, Saad and Hafsa, any doubt, any question? Yes, you guys can ask me if you guys have any question. And Hafsa, for you, I will take some backup classes. Okay, because you are joining just now. So let's see what we can do. And guys, Saturday we'll have an extra. So from this Saturday onwards, we will have extra classes. Okay, guys, on Saturday.
Yes, sir.
And yeah, and you guys decide the timing. So you guys have Thursday, right, to decide what would be the time. Okay, you guys. So that would be before 4 p.m. KSA. So before 4 p.m. KSA, that can be 2 p.m., 1:32, right? That would be. So you guys decide what is feasible to you, 1:30 or 2, or yeah, 1:30 or 2, or 2:30 also. So whatever is feasible to you guys. Okay. And why we are taking these extra classes so that we can complete before the end of July. Yeah, so before the end of the July, we can complete these third chapter also. So if all these three chapters are completed, then we would be revising, right? Because so at that time we have our lunch, lunch as in school lunch or home lunch. Yes, home lunch. So at what time, Maria? 1:30 or 2 or 2:30? When did you guys like around 2? Okay, so then 2:30 would be possible, right? If you have lunch at 2, so 2:30 would be possible then, right? Because I want to complete the syllabus. Yeah, 9:30 KSA. So 9:30 KSA would mean that 12 p.m. in here. But our classes ends at what, 7 p.m. KSA. So yeah, then that would be because 12 p.m. IST would be right, 12 p.m., 12 to 1. So I need some sleep, guys, right? If I sleep at 12 p.m. or 1 p.m., then I would not be able to wake up. So yeah, that can be done only in yeah, that can be done only in morning. Okay, so morning, before 6:30 p.m. KSA. So at 9 p.m. Saturday we have I have some class at 9 p.m. IST. So again, that is why in the morning that can be possible. So you guys decide from uh, from 11 a.m. from 11 a.m. to what? From 11 a.m. to whatever, mm, 2:30 p.m. So in between these timing, you guys decide. Otherwise, we won't be able to complete the syllabus. Okay, so before let's come back to this. So we were calculating the potential energy of a dipole in external electric field. Right. So this would be how much? We have a uniform electric field, okay? And then we have a dipole. But before I calculate that, you guys tell me what is the potential energy of a dipole. So this is minus Q, this is Q, and this is 2A. What would be the potential energy of this dipole? Yes. Yeah, K, Q minus by this 2A. Right, so minus KQ square by 2A. Right, and this minus signifies that they are bounded. So minus signifies bounded and positive signifies that they are unbounded. Okay. Yeah. So this would be the potential energy of a dipole. Now, what would be the potential energy of a dipole in external electric field? So we have this dipole, right? And this is minus Q. This is a Q. So work done, right? Work done would be due to let's say that work done due to this, let's say this is theta. So we have this theta 1 and then we have this theta 2. I will talk about theta 1, theta 2 later. But we have this Q and minus Q and a Q charge. So this is a dipole, right? This is making an angle theta with the electric field. So, Mariam, you tell me at this point, what is the force at this point? Mariam, tell me what is the force at this point? Hmm. Aisha, you tell me what is the force at this point? Yes. What is the force at this point? This is placed in some electric field. So what is the force at this point? Saad, you guys are telling me the answer or yeah. Yes, Mariam, Saad, and Aisha. You guys have forgotten or what? So I am asking that if I have this electric field, right? I have this electric field and I have put some charge in here. So what would be the force on this charge? We have done so many calculations based on this concept. QE, right? So yeah, Mariam, oh, you said QQ by R square. Okay, so we don't know what is the distance, Mariam, right? We don't know about the distance. So we only know that there is some electric field. Yes, Aisha, right answer. So this would be F would be simply QE, right? And if I have a negative charge, so F would be in this direction, minus QE. So this we have done so many times, right? So do you guys remember now? This is the force on a charged particle in external field. So this would be the answer. Understood, Mariam? Yes. Yeah. So Mariam, please work on your mic because yeah, your voice is very faint. Aisha and Saad, did you were you able to listen what Mariam was saying?
No, sir.
Yeah. So yes, Mariam, please fix your mic. Yeah. So Saad, you have returned. Yeah. So now do you remember, Saad, the force on this charge particle in external field? Right. This would be QE. And if we have negative charge, so this would be minus Q in this direction. So similarly, on this charge, we have force equal to QE in this direction. Right. And then we have some force on this charge. This is minus. So minus QE. Right. So we have F net, which is QE and minus Q. Right. So this cancels and F net is 0. So would the work done would be possible if your so what would be the work done due to this force? Yeah,
Zero.
work done 0. So for this force, the work done would be 0, right? But we have another force, right? What kind of force? So this is due to the translational force. But we have another force that is acting on this dipole. So if you guys remember that, let's let's see who remembers. Aisha, what is the other force that we have? Yeah, Mariam, what is the other force that we have? So translation force is 0. F net is 0. What is the other force that we have? No, 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 not the Coulomb force. This was the Coulomb force, right? F and F between. So one is translation force, right? So we have a dipole, which is this is the electric field, and one force is acting like this way. So if those two forces are acting, so there would be another force which is created. Rotational force, yes, rotational force. That is torque. right? Rotational force, that is torque. So there will be some torque, right? So if there is some torque, then there would be some work done due to this torque, right? So work done due to this translation force would be zero, but we are moving this dipole. We are moving this dipole, right? But this movement is rotational. So we are changing the angle of this dipole. Angular distance is changed. So if angular distance is changed, then there would be some work done. So for this part, there is no translational distance, right? Because we are in uniform electric field and F net is zero. So there is no displacement in translational part. But we have a rotational, yes. So, okay. So this is the dipole, right? This is the dipole, and same amount of force is acting in this direction and same amount of force is acting in this direction, right? So this is not moving in this way, in this direction or in this direction. So there is no displacement in this direction and there is no displacement in this direction. So displacement is zero, F net is zero. So work done by this displacement is zero. But this force is making some rotational force, right? So your theta is changing. So let's say that this was theta, so this theta has been changed to this one, right? So this theta, this is the theta, and this theta has been changed to this theta. So due to the angular displacement, we have angular displacement. So due to the angular displacement, there would be some work done. Whenever some external force is applied, external torque is applied, right? There would be some angular displacement. So due to that angular displacement, there would be what? There would be some work done. So work done would be angular displacement, which is torque, right? Angular force, and this is external dot d theta. Is that clear? Is this clear, guys?
Yes, sir.
Yeah. So because this work done would be zero, but we have the work done due to this change in angle. Okay. And let's say that if you guys remember or not. So what was the torque or on dipole due to electric field? Yeah, what was the torque on dipole due to electric field? Anybody remembers? What was the torque? Anybody remembers? Oh, who got disconnected? Oh, yeah. So QE sine theta. Yes, yes. QE sine theta or close. Yes, yes. Bayam has got the right answer. Yes, Aisha, you were close. So this was P cross E, right? Which is PE sine theta and n cap. So let's take the magnitude only. So magnitude is PE sine theta. And this is due to this electric field, right? So if we want to some work done, which is some external work done, right? Work done in moving a charge from theta 1 to theta 2. So this torque external would be how much? This T ext would be minus of T electric field. Okay. So this would be how much? This would be T ext would be PE sine theta. And let's take the mod. Let's take the positive sign. Or if we write, then we can write this also. So this is minus PE sine theta. Okay. Is that clear?
Yes, sir.
Yeah. So this is minus PE sine theta. And we have to apply this torque. This is the electric field torque, but we will apply the torque in this direction, right? So if we apply the torque in this direction, tau external, and the angle is this one, so they are opposite, right? Who got okay, Saad got disconnected. So then the angle between torque external and d theta is what? 180-degree, right? This is in this way, this is in this way. So 180-degree, which means that tau external d theta cos of 180, right? This is theta 1, this is theta 2. So this tau external is minus PE sine theta. Cos 180 is again minus. So minus and theta 1, theta 2, PE sine theta, d theta. So this is the work, external work. Okay. Is this clear, guys? Is this clear? So work done would be theta 1, theta 2, PER, uniform integration of sine theta, d theta. So what is the integration of sine theta? Yes, what is the integration of sine? Yeah, minus cos theta, right? Minus cos theta, and then we put the limit. So theta 1, theta 2. So this would be how much? Minus PE cos theta 2 minus cos theta 1. So this is the work done in some external. Okay. And we know that from work energy theorem that work is a change in potential energy. Okay. So if theta 1 is, let's say that if this is the electric field, right? And if theta is, let's say that, so let's say that theta 2 is, my theta 1 was, let's say this one. So theta 1 was 90-degree, right? And then theta 2 is, let's say some theta. So what would, let's say theta 1 is 90-degree, and at this potential is, let's say 0, right? And then theta 2 is some theta. So then this potential is some u, right? So then my potential energy would be what? This would be work external would be change in potential energy, which is u minus 0, which is PE cos theta. Okay. So PE cos theta would be how much? So this is u is minus PE cos theta. And what gives you AB cos theta? What gives you AB cos theta? Which product gives you AB cos theta? Yes. Which product gives you AB cos theta? Yes, cos theta, cos theta. So you have two kinds of, which vector product gives you cos theta? So let me simplify the question. Rectangular, rectangular product is what, Mariam? So you have two kinds of product, vector product, scalar product. What product gives you cos theta? Scalar product, right? So A dot B gives you AB cos theta. So we have PE cos theta, which means that minus of P dot E. This is the potential energy. Okay. So you see that torque is how much? Torque is P cross E, and potential energy is minus P dot E. Is that understood, guys? Yes. Yeah. What did you say? Your voice is not clear, Mariam. What did you say? I was not able to understand. Yeah. Mm. Yes. What did you say? AB cos theta. Yeah. So, what is the dot product? Dot product, let's say P dot E would be how much? This would be P E cos theta, right? So I have this PE cos theta. Okay. I have this PE cos theta, so I can write PA cos theta as P dot E. Right? Yeah, so that is what I was saying. So any doubt up to this point, guys? Any doubt? Theta is 180 above. Okay. So you see that torque for this part, right? So this is the theta angle. This is the angular displacement, and this is the torque that we are applying. So if this torque is in this direction, and theta is in this direction. So we have how much angle? 180 degree, right? Cos theta is 180 degree. So P cross E. This gives you the angle of torque, right? So this is P, right? This is P, and E is in this direction. So P cross E is in this direction, downward. P cross E is in this direction, downward, and theta. So I'm going theta. Theta is upward. Okay. Theta is upward direction, and P cross E is downward. So what is the angle between torque and the angular displacement? Yes, 180, right? So this is how it is 180. Understood? Okay, so yeah, any more doubt, guys? Do you guys have any more doubt? Yes. Any more doubt, guys? Okay, so yeah, please note down from this point. So this you guys have noted. So please note down from this point. Yes, Saad and Hafsa. Any doubt? Yeah, this is top. So Saad and Hafsa, do you guys have any doubt? I can explain it again. So don't bother about that. I have to repeat. Yes. So whenever you guys need me to scroll down the screen, you guys tell me. Okay. Yeah. So Hafsa, you see that we have a dipole. Okay. We have a dipole, right? We have a dipole and we want to calculate the potential energy of this dipole, which is placed in some electric field, right? So we have already calculated that we need to calculate the work done. If we want to calculate the potential energy, so from work energy theorem, we know that if we calculate the work done, then we'd be able to calculate the potential energy. So this was our goal, right? Now we have to identify that what kind of work done is being there. So what kind of force is there, which is doing the work. So we saw that this translation force will not do any work because this net force is zero and we don't have any translation motion. We only have rotational motion. So rotational motion means that we have some angular displacement. So from this angle, let's say this is theta 1, this has been moved to this angle, right? So this is theta 2. So now we have made some angular displacement due to some external torque, right? We are applying some external torque and then we are rotating this thing, this dipole. So this will do some external work, right? So then we calculate this external work, okay. And then we found out that this external work would be this quantity. So this was the whole idea. The rest is the solving part, simplification. The idea is only this, that this work done would be just, this work done would be due to this external torque, not some external force. So is this part, is that clear to you now, Hafsa? Yeah. Okay, so at which point you guys have noted? So we have to be quick so that we can just complete. Yeah. So where should I put the screen? Is this okay?
That is fine.
Scroll down or up? What did you say?
So it is fine.
Oh, it is fine. Oh, yeah. You guys quickly note it down because in today's class I want to reach capacitance and. So you guys remember that I have not talked about the equipotential surface. And one more topic I will not talk about. I will just give you, I will make a video and then just send you that because those are mainly theoretical part. Equipotential surface and properties of the conductor. So there are only properties that we have to learn, right? Okay, so should I scroll down the screen?
Yes, sir.
Oh, this ends here. Yeah, so 7, we have only half an hour. Guys, be quick. Okay, who got disconnected? Saad got disconnected. And also Mariam is not here. What is happening?
Fine, sir.
Done. Hafsa noted.
Yes, sir.
Okay, so please let us wait for Mariam if she has. Yes, Mariam, did you note down this part?
Yes, sir.
Okay, so there is a question that we know that what would be the work done? Work done would be minus PE cos theta 2 minus cos theta 1. So just remember this result. And then you have the potential energy, which is minus of P dot. So just remember this result also. Okay, so then this will give you the answer. Yes, and this work done is equal to this change in energy. So these are three things you guys remember. There is a question that what would be the work done in bringing some charge or bringing a dipole from stable equilibrium to unstable equilibrium. So if you guys remember that what is stable equilibrium, okay, I will talk about that question later. I have to, yeah, just skip that part and let me go to this potential due to a hollow sphere. Right. So we have a sphere and this this is a hollow sphere. So all the charges will reside on the surface only. There would be no charge inside. Okay. So let's say that this charge is Q. So there are three regions, right? One is this inside. This is a surface, and the radius of this hollow sphere is R. Okay. And then we have this outside region. So we have to just remember that what would be the potential due to all these, or what would be the potential in these three regions. So one, this is two, and this is three. So just remember this formula that V inside would be simply KQ by R. Okay. V at surface would be KQ by R. So you see that, you guys see that this is a fixed quantity, right? This R is fixed. The radius of this hollow sphere is fixed. So the potential at this point, at this point, at this point, at this point, or at surface, all these potential would be the same, right? You don't, yeah, you guys don't be confused that if we have this electric field which is zero inside. So what is the charge inside? Yeah. What is the charge inside this sphere? So zero, right? But you see that potential inside this hollow sphere would not be zero. We have charge which is zero. We have electric field which is zero. But the potential inside this hollow sphere would be this. Okay. And then we have V outside. So this would be KQ by R. So these are three results you guys just remember. And what is the graph of this? What is the graph of this potential? So we have R, we have this V, okay. And this is, let's say, this is the surface. So up to surface, you guys see that this would be constant, okay, which is how much? Which is KQ by R. And then it decreases. Okay, so the graph of a hollow sphere is this. So this is the R equal to R surface, and this is the outside. So this is the outside region, And for the outside region, this varies as 1 over r. And this is the surface, and this is inside. So inside is constant, and this is fixed, and then it is reduces. So is this part clear, guys? Potential due to a hollow sphere, is this clear?
Probably explain the inside again.
Yeah. So for the inside, just you accept that there is a reason that why this is KQ by R. Because if you guys remember, what is the potential? Can you guys recall that? Aisha, can you recall what is the potential? Hmm. So what is the potential?
Will you repeat your question?
Yeah, what is the potential? What is the definition of the potential? Yeah, what is the definition of the potential?
Work done and you begin
Yes,
discharge from
yes,
infinity to a point.
yeah. This is the right. So yeah, if and then this is equal to what? Minus of E dot dr from infinity to, let's say, point whatever we are calculating r. Right. This is the integral. So you see that if we calculate, this was not a part of the syllabus, but for the understanding, let us just understand that. If we calculate the potential in inside, so let's say that this is some small r, right? This is inside and we are calculating at this point. Okay. So at this point, the integral would be of two parts. So one would be infinity to r e dot dr, and then from p to from r to this small r, e dot dr. Is this clear? Because we are calculating from infinity to this part, right?
Yes.
So this portion would give you 0, but this integral would give you how much? KQ by R. Is this clear to you now? And this
Yes.
part, yeah, this is E equals to 0. In this region, from R to R, E is 0, so this part will give you 0. But this part will contribute from infinity to this part. From infinity to this R part, this will contribute and this part will contribute to 0. So that is why we have this constant electric field. Is this clear?
Yes.
Yeah, you guys quickly. So Hafsa and Mariam, do you guys have any doubt? Yeah. So please, so just understand that for hollow sphere, at every point and at the surface, the potential is same, right? And that is how much? KQ by R. This is fixed inside and at the surface. Whenever we want to calculate the potential at this part, at this R part, so this is simply KQ by R. Yes, whenever you guys have noted it down, please tell me so that we can, yeah, then we'll start the new topic. And in Thursday, yeah, I will, okay, so yeah, I will see that how much we can complete. And then on Saturday, we will have a class. So on Saturday at 2:30 p.m. KSA. And yeah, Mariam, could you please yeah, shift your lunch time, because then Otherwise, it would be a problem. So please shift your lunch time. Just quickly finish your lunch and then, yeah, come to the class. So 2:30 p.m. KSA, which means 2:30. So 5. Oh, 5 p.m. KSA. So 5 to 6. Okay. Yeah. Oh, we can do 12 morning KSA. So 12. So 12 to 1. Is that okay with everybody? 12 KSA? Oh, good, good. So Hafsa, is this okay for you? 12 KSA. Yeah. Only up till only until your school opens, because yeah. So after your school is has opened, then we won't be able to take these extra classes, right? But before your school reopens, then we can take these classes so that we can complete the syllabus. Yeah, so 12 KSA meaning 2:30 IST. Good, good. 2:30 IST. So this is very good for me. 2:30. Thank you guys. Yeah, for cooperating. So noted everybody this part.
Yes, sir.
Okay, so let us quickly go ahead and start the new topic, which is capacitance. So, and there would be a class assessment test, right? So you guys, please take that test. I'll be taking some other class, so but you will have some waiting room. Go into that waiting room and take that class. Take that test. Okay, so what is capacitance? So it is the charge holding capacity of a conductor. Okay, so this is the charge. How much charge can hold a conductor can hold? This is called the charge. That is called the capacitance. Okay, and when we plot the graph, so this Q is directly proportional to V. Okay, so when we remove this proportionality, so then this comes, right, and then C is your Q by V. Okay, so this is called the capacitance. So this constant is called the capacitance. Okay,
Yes,
so is
sir.
yeah, and yeah, and what is the this is a scalar quantity. This is a scalar quantity, and the SI unit of capacitance is what? So you guys can see that Q is what? Coulomb, right? V is volt. So Coulomb per volt, or we can also write it as Farad, right? Farad, which is represented by F. So this is the SI unit of what capacitance. Okay. And the graph of, so this capacitance only depends upon the geometry. So it only depends on geometry. And it is independent of Q and V. Okay, so if we have let's say volt and Q graph, so this would be constant, right? So this tells you that this is a constant graph. So this doesn't depend upon uh, yeah. So Q by V would be constant. Is this clear?
Yes.
Oh no, no, not this one, but C is constant, right? So C, or let's say that if you are this is your charge is changing, so this would also be constant. Okay. If you change the charge, so C will not change. This will again be constant. Okay, we want one. So Y is mx, right? And if Y is not changing, yeah. So Q is CV. Okay, so Q is CV, which means that Q by V, Y is mx. So Y by X is M. So yeah, Q, so we can write Q and V. Right, then Q is what CV, so we can make this graph. Okay, so Q by V would be constant. Yeah, you guys note it down. So quickly, any doubt up to this point? So these are some definitions only. Yeah, so just quickly note it down, and then we'll talk about, yeah, then we'll talk about the next topic. Done.
Also,
Yes, noted everybody.
yes.
Yeah, so okay, so now the next topic is capacitor. So we understood about capacitance. Now the next topic is capacitor. So capacitor is what? Capacitor is energy storing device, right? So this is an energy storing device, and there are three kinds of capacitor. Okay, so these are capacitor is a device. capacitance is a property. Capacitor is a device. Okay, which uses the property of the capacitance, right? So capacitor is energy storing device, and there are three kinds of capacitor. One is this parallel plate capacitor. Okay, yeah, and then we have this spherical plate capacitor, or spherical capacitor, and then we have this cylindrical capacitor. Okay, so this cylindrical is not in the CBSE syllabus, so we will not talk about that. Okay, and yeah, so this we'll talk about parallel plate capacitor. We'll talk about in detail. Okay, so but before we do that, let us calculate the capacitance of a capacitance of a hollow sphere. Right. So we have a hollow sphere. Okay. So let's say this is right. And we want to calculate the capacitance of this hollow sphere. So the charge is Q, and potential is how much? Potential is KQ by R. Right. So the capacitance is how much? Q by V. Right. So Q is Q, and this is KQ by R. So this would be how much? So this R goes in the numerator, and this K is 1 by 4 pi epsilon naught. And this is Q. So Q cancel, and capacitance of a hollow sphere is how much? This is 4 pi epsilon naught R. So this is the capacitance of a hollow sphere. Okay. So yeah, you guys note up to this point, and then just quickly note up to this point, and then we will talk about parallel plate capacitors. Whenever you guys have noted down, please tell me. So in parallel plate capacitor, I will see that how much you guys remember about the electric field. So noted up to this point.
Done, sir.
Okay, so yeah. Hafsa and Mariam, noted. Hafsa, what about you? Noted. Okay, so now let us talk about the parallel plate capacitor in more detail. So we have a parallel plate capacitor. So we have this plate which is positive, right? And this is negative. And positive is connected with a positive and negative is connected with negative. So this is some V volt. So in this we have some V volt. Okay. So you guys, if you guys remember, so what is the electric field of the sheet? What was the electric field of the sheet? Yeah, let's say this is plus. So what was the electric field of the sheet? Aisha? Yes, what was the electric field of the sheet?
Sigma
Rem-
by 2 epsilon.
Yes, yes, yeah. So sigma, good. So sigma by 2 epsilon, right? And in this direction also we have sigma by 2 epsilon, right? So is this correct, Mariam and Hafsa? Yeah, and for the negative one, the electric field will be in this way, right? Direction would be this, but magnitude would be same. So 2 epsilon. Is this clear? Yes.
Yes.
Yeah. So for the case of the parallel plate capacitor, for the place of the case of parallel plate capacitor, so the electric field of this plus would be E plus, right, in this way. So E plus would be in this way for this region, E plus would be in this way, and in this region, E plus would be in this direction. Okay, and this is minus. So E minus would be in this direction, E minus would be in this direction, and in this way, E minus in this direction. So this part and this part cancels, and only this part will add up. So electric field would be E plus and plus E minus, which is sigma by 2 epsilon naught sigma by 2 epsilon, which is sigma by 2 epsilon, sigma by epsilon, right? So this is 2 into sigma by 2 epsilon naught. So sigma by epsilon. This is the electric field inside. And outside is 0, right? This part is in this direction, this is in this direction. So cancels. Similar in this way. So only the inside part will survive, right? Is this clear?
Yes, sir.
So electric field is sigma by epsilon naught, and electric field is related with potential. So this is minus delta V by delta R, right? So if I take the positive value only, so this is delta V by delta R. And this distance is D, and voltage is V. So this would be equal to V by D only. So electric field is how much? V by D, right? Is this clear? Yes.
Sir, could you explain again?
Yeah. So the distance between these plates is D, right? And the voltage between these plates is V. So delta V is V, and distance with R is this T. Okay. Because we know that E is the gradient of potential, right? This we know. And we can write this as minus delta V by delta R, right? So if we take the mod, which gives you the positive value only, so this will be V by D. And electric field is potential by the distance, right? So is this clear now? Who got disconnected? Oh, Mariam got disconnected. So is this clear now, Aisha?
Yes, sir.
Okay. So electric field is V by D. Electric field is sigma by epsilon naught, and Q is how much? Let's say charge is Q. Okay. So let's uh, let's leave it at that. And the area of the area of this plate is let's say A. Okay. Area is similar. So we have this sheet or plate. So and its area is A. Okay. So you guys, yeah, you guys tell me that how sigma charge and area are related. How these three quantities are related. Yes. How sigma, which is surface charge density, charge and area are related. Hmm. When I was talking about the continuous charge distribution. So how?
Is
Yes.
equal to Q by
Yes. So sigma is Q by A. Okay. So I can calculate, I should write it here. So sigma is Q by A. So Q is sigma into A. So this part we have calculated we know E is this, and we can write V as E into D. Okay, from here. So now what is capacitance? Capacitance is what? This is
Q by
Q by V, right? And Q and V is ED. We have just calculated. And E we have calculated, which is sigma by epsilon naught into D. Okay. And sigma again we have calculated, or Q we have calculated, which is sigma A. So sigma A, sigma D, and this goes in the numerator. So sigma cancels and capacitance is A E epsilon naught by D. Right. So this is the capacitance of a parallel plate capacitor. Is this clear, guys? Any doubt?
no sir.
Okay. So you see that this capacitance doesn't depend upon the charge. This doesn't depend upon the voltage. This only depends upon the geometry of the parallel plate. Right. So distance between the plate and the area of the plate. So yeah. You guys, please note down from here. And if you guys have any doubt or if you want me to explain it again, so you can tell me. Yeah, so whenever you guys need me to scroll down the screen, you guys tell me. So parallel plate, I have finished, and then I will talk about the combination of capacitors. So yeah, this is the combination of then we'll be able to, then we'll calculate the energy of the capacitors, and then that would be all. So this second chapter would be finished. In the next two classes, this chapter would be finished, and then we will start the, yeah. So then we'll start the next chapter, which is current and electricity. So should I scroll down the screen, guys?
Yes.
You guys can ask me question if you have any doubt. So if you have any doubt, you guys can ask me. Yes, Hafsa and Mariam. Any doubt? And yes, Hafsa, I will take some backup classes for you because you have already missed the first chapter and the half portion of the second chapter. So we'll try to cover that up. Okay. So whenever you guys have noted down, yeah, please tell me. And again, Saad got disconnected. Mhm. So I don't know how I will be able to complete Saad's syllabus. Whenever you guys have completed, please tell me. Finished.
Done,
Aisha
sir.
and Hafsha, what about you, Hafsa? Yes, Hafsa, done.
Yes, sir.
Okay, so now what we calculated, we had a parallel plate capacitor, right? And we saw that only the electric field inside this region survives. Outside portion, this portion cancels out. But we calculated the capacitance of this parallel plate capacitor uh, so there was nothing inside this capacitor, right? So the medium was air between these plates. But what we do in the next part, so we put some dielectric. Okay, so we put some dielectric between these. So if you guys remember that whenever we put some dielectric, then the force decreases or increases. Yeah. So in Coulomb's law, we learned that whenever we put two charges in some dielectric, then what happens to the Coulomb force? So 1 by 4 pi epsilon naught, and this is Q1, Q2 by R square. So this was air. But whenever I put it in the medium, so this becomes 1 by 4 pi E, right? Q1, Q2 by R square, which becomes 1 by 4 pi epsilon naught K, and then Q1, Q2 by R square. So this is the dielectric constant. And we see that this F air by K. So this medium decreases the force, right? So similarly, what we do is that we just replace this epsilon with epsilon naught K. So what was the electric field in the case? Let's say that its dielectric constant is K. Okay. And separation is again same. So this is D, right? And then we have sigma, which is, and area is same. So area is A. So electric field would be how much? Electric field was sigma by epsilon naught. But now the electric field would become how much? Right, guys?
Yes.
So, yeah, parallel plate capacitor in a medium, dielectric medium. Okay, so did yeah, Rifa has not joined yet, so we can extend some portion. So this electric field would be right decreased by what factor? By this K factor, dielectric constant. And now what we know that this electric field is related to this potential. So this is V by D, right? And V is ED, which means that this is sigma by epsilon naught K into D. Okay, so this is the potential, and what is the capacitance? So this is Q by V, right? So Q by V, which is sigma D by epsilon naught K. And again, Q is sigma A into epsilon naught K divided by sigma into D. So this cancels, and the capacitance would be how much? So this would be A E epsilon naught K by D. So you see that this K factor is the extra part. So the capacitance would increase. Whenever we put the parallel plate capacitor, so whenever we put some dielectric medium in between the parallel plate capacitor, so the capacitance will increase. Is this clear? Yes.
Yes, sir.
Okay, so please quickly note it down. And then there would be there's one more type of question. Okay, so that I will talk about in the next class. So you guys please revise these portion. Otherwise, you guys will forget. So please revise. Okay. Yeah. So and yeah, log into the Learnivio account. Open the uh, class assessment section, and then you will find some tests. So let me ask that. Um, yeah. So did you guys log into your account? Oh, but before that, you have to. Yeah, you have to. So did you guys note down up to this point?
Yes, sir. Can you scroll?
Yeah. So please note it down. Oh, yeah. Rifa has. Okay, so you guys please log in and complete it, guys.
Yes, sir.
Yeah. Hafsa and Mariam, completed. Yes. Yeah, so there is a small correction, guys. There is a small correction in the graph. So in the graph, there this would be again. So the part that I wrote earlier. So this is C, and please correct this. And again we have C and Q, because this C is constant with Q and C is constant with V. So this is the graph. Please correct it. And go to the waiting room. Okay, so go to the waiting room, and then yeah, take that test. Log into the account and take that test. So how many people do we have? So yeah, did you guys corrected this portion?
Yes, sir.
And yeah, open the Learnivio account and then take that test. Okay. Yeah, did you guys open open the Learnivio account, and yeah, you will find the. So Hafsa, do you have the Learnivio account? Yes, Hafsa, do you have the Learnivio account? Yeah, so please log into an account and then you will find some active test. Okay. In the class assessment section, you will find some active test. So you guys please take that test, and yeah, so one other student is waiting. So yeah, you guys, okay, she has joined. So yes, please, did you guys log in?
Yes, sir.
Yeah, then did you find that test?
Yes, sir.
Okay. Yes, hello, Rifa. Good evening, good night. Yeah, good evening, I guess. Yes, hello, Rifa. Am I audible? One moment, one moment.